Okay, there we go. Had to talk it into focusing, but that actually worked. Okay. So again, let's just see what we're talking about here. A couple of leads. Yeah. Still one here. Okay. I think I've got another thing. Okay, so here's what we've got. We got this set of Helmholtz coils, and we can run current through them and create a pretty substantial magnetic field without a whole lot of voltage. Okay. Now I'm saying 4 millitesla. That might be right. It might have been 0.4. I don't remember. We'll work it out in a minute because we kind of know what our current was and so forth. Okay. So anyhow, here it is. Now, inside, you see rattling around there, this piece of 6-inch sewer pipe that has loops of wire around it. Okay. And when we run a current through the Helmholtz coils, the outer coils, and when we change the current, that changes the magnetic flux, the magnetic field within the inner loop, therefore the magnetic flux. And when the magnetic flux changes, you get an EMF around the loop. Okay, so we're just going to look at one single loop. And just make sure we have our handle on what we've got here. Now, the thinking I'm saying out there is pretty good. So, you know, what do you need? What's going on here? And so forth. And somebody said Lenz's law. Now, one disadvantage of that is you then immediately start thinking about a formula instead of what's going on. Okay. But I think you're thinking about what's going on too. So I want to focus on what's going on. Formula comes from what's going on. If you just understand things at a more fundamental level, you don't need the stupid formula. Okay. It's not a stupid formula. It's one of the great formulas in physics, but it's unnecessary if you understand the details. Okay. So we're going to assume a 4 millitesla field inside the coil. I think it was more like 0.4, but it might have been 4. Okay. But with what we're using to accelerate it, we're going to test, see whether that's reasonable. So we got this field inside the coils, and there's I call it a free loop inside, meaning it's not attached to the circuit consisting of the coils, okay? It's just in there. And it's implicit from what you just saw that the coils, the outer coils for the Helmholtz coil are in essentially the same plane or in planes parallel to the loops around the 6-inch pipe. Okay, so let's assume that all these loops are parallel. In other words, they have a common normal vector and all that stuff. Okay, so we got this field, the inside diameter. Well, it's 6-inch pipe. I say it's 15 centimeters. Now, pipe has some thickness. It's 15 centimeters. It's the inside diameter. Okay, so I'd say if you want to be really careful, it's going to be between 15 and 16 centimeters. And actually, I think I cut this out of the flared end of a piece of sewer pipe, okay? Which had never been used as sewer pipe. I still washed it for everybody so nobody get grossed out. Just been laying around waiting to be used for 40 years, okay? So that diameter might have been even 17 centimeters when we cut down to it. But let's go to 15 centimeters, it's an easy number to work with. And you're not going to get that big a difference. freeze of 17 centimeters until we try to get really precise with the change in the field. How quickly does the change in the field occur? Well, anyhow, if the field suddenly reverses, we want then the EMF around the loop. By the loop, I mean this loop, not the coils, the loop. And then what's the electric field in the loop? Well, all that is stuff that you can easily do from the transition problems and are doing pretty well. Okay, doing pretty well with this. Okay, so first of all, the field's perpendicular to the coil and to the loop because these things are all in parallel planes. Okay, now if I start tilting that loop inside, couldn't tilt it much because it fits fairly tight. Right. Wire came loose, so we got to fix that. But anyhow, a piece of tape. So we have this information. Well, we can just start by finding what creates the EMF. Okay, EMF is created by a changing magnetic flux through the loop. Now, one approximating assumption that we're going to make here is that the field is uniform throughout that whole loop. Now, we could actually do some multivariable calculus with the fundamental rules, the fundamental relationships, a current I in a segment delta L creates a field at point P due to the R vector and the cross product of the IDL and the R vector and all that stuff, okay? Which we talked about a few weeks ago. Then we'll talk about it now in such a way that you're going to really lock it in and make it rigorous. We could set that up for any point in the vicinity of those two coils. We probably couldn't do the integrals, so we'd have to go to integral approximations. And it might be interesting to do that, something that I kind of find entertaining and fun to do. We probably don't have time. Although if people just get down their knees and beg me, maybe we will. Be a good exercise. The reason I say that is we could see, and of course we'd want to simulate this on a computer where we could just put in the coordinates of the point and determine what the magnitude and direction of the field is at that point. And we explore around a few points and see how nearly uniform it is. Maybe sample it, maybe write the program to sample it. All kinds of neat things you should do to figure out what the actual magnetic flux through that loop should be. Right now, we're just going to assume that it's the same as the field at the center of the coil. Okay? And whatever that is, it's what we measure. And that's going to be our formula testing. Maybe it's formula testing. We'll figure out which is more reasonable. Okay? So we get the EMF created by changing magnetic flux through the loop. The flux, which I'll call phi sub B, is the loop area times the magnetic field, which is, okay, 15 centimeter loop. Now I'm just going to approximate this. It's fine, put the numbers into formula, plug it in, and see how close everything is. I just approximate because I don't know exactly what the area or what the actual diameter of those things is. So a good ballpark approximation is going to be sufficient. a square 15 centimeters on the side, 15 square being 225, has an area of 225 square centimeters. Pi over 4 is pretty close to 3/4, a little bit more than 3/4. Okay. And 3/4 of 200 is 150. Okay. 3/4 of 25 is 18.75, about 170 square centimeters. So I'm going to say this is approximately 170 square centimeters times 4 millitesla. Meters squared. Okay. Because a centimeter is 0.01 meter. And when you square 0.01 meter, you get 0.0001, which means you're going to move a decimal over 4 places to get that. Or you can just have developed the intuition to do that correctly. Although you always want to check yourself. I pretty much have that intuition, but I still screw it up a lot of times. So that's going to be like 0.07, 0.068. Tesla meter squared. Now, this doesn't have an arrow over it, so it's just the magnitude of the flux. So the first thing I want to think about when I look at this is how much flux are we getting through this when you got 4 millitesla? Okay. Now, you can talk about cosine theta. You want to use cosine theta, cosine theta, cosine theta. That's fine. Theta's the angle between the normal vector and the field. They're parallel. Okay. So cosine theta is going to be 1 or -1, depending whether the field's in the direction of or direction opposite your normal. Okay. So these parallel to the normal to the loop. V reverses. So the magnitude of change in the magnetic field is 2 times 0.07 Tesla meter squared. Like field's parallel to the normal, it's 0.07 Tesla meter squared. When it reverses, it's negative 0.07 Tesla meter squared. Okay. The difference between 0.07 Tesla meter squared and negative 0.07 Tesla meter squared is -2 times 0.07 Tesla meter squared. I'm just talking about the magnitude of this. It doesn't matter if it's positive or negative. It's 0.14 Tesla meter squared. And that's totally could be 0.007. Okay. So let's just check that out. This is on the order of a square meter. I'm getting like 2 thousandths. I'm not seeing where that's wrong. Anyhow, let's pretend these numbers are right. Because we're interested in the process. And we can then modify our number. That seems a little high, because when I divide that by like 400ths of a second, got to get a significant fraction of a volt, and what we actually saw in the interface is in the millivolt range. Okay, so that disturbs me a little bit, but let's move on. Okay. Reverse, and there's an E in there. Okay. Now, you estimated that I was able to reverse the field in 400ths of a second. Yeah, I think that's not too far off. I don't think I was quite that quick. Probably more like 1/10 of a second, but we could look at the display and see how wide that spike is. And we can figure it out pretty easily. So if it's reversed in 400ths of a second, then the EMF average will be approximately 0.014 Tesla meters squared over seconds, which is approximately 1/3. Then you ask, okay, so just tangentially, what's the electric field in that loop? So the average of the electric field in that loop is the average of your EMF. So we'll get this too bizarre. The average of your EMF divided by the circumference of the loop. So the loop, because the voltage, that 1/3 of a volt, is spread out over the circumference of that loop of diameter approximately 15 centimeters. So that circumference is ballpark 50 centimeters. Okay, it's going to be pi times the radius, a little over 3 times 15, 45, a little over that. It's close enough to 50. So we get 1/3 of a volt, 50 centimeters, which is 0.5 meters. That comes out to be about 2/3 Newton per Coulomb. Okay, so we're getting an electric field in that wire on the order of 2/3 of a Newton per Coulomb. It's a ballpark Newton per Coulomb because, that 4.04 seconds is pretty fuzzy. So we think we're getting a field of around a Newton per Coulomb. So what can we do with that? We can get our current density. Okay. Density. It's going to be electric field times conductance, right? Which would be electric field of resistivity, etc. Okay, back to that model. So we could estimate permanent otherwise. We can also find the resistance of that wire from its diameter and its length. You know, half a meter of wire of that diameter, which is probably around half a millimeter. Okay. We could use our formula for resistance. But we really want to understand in terms of conductivity. Okay. Conductivity just being the reciprocal resistivity. All right, so we can experiment with all that. We can actually set this up and put a 9-volt battery in series. We could use a filtered power source, but I'm not sure how good those things are. 60 years old by now, close to. Okay. And I'm not sure I want to set you loose to something you can shock yourself seriously with. Okay. We can learn what we want to learn here. And then we can use a function generator to generate waveforms and investigate RC and RLC circuits. Kind of what our program is for the rest of this month. All right. If we get something that looks like this, have an amplitude that we can measure. So we have voltage in this direction, time in this direction. We can measure the width here. Delta T. I don't think this would be exactly a linear spike. I think it tend to be maybe more Gaussian, but I haven't thought that through, so I'm not even gonna speculate beyond the fact that that's worth thinking through a little bit more. I'll try to do that. Okay. But we've got a delta T here. What's our average voltage? Well, we just take the area under this spike and divide by delta T and get an average voltage there, right? We'll have a peak voltage and an average voltage. Now the average voltage probably going to be down around here. Although if it's a sine wave, it'll be something a little bit different. Sine wave, you can do the integral, figure out what the average value is. Okay. Not difficult to do. But we can get into all those things. But the fundamental thing is what happens when you change the flux inside the region. Now, what would happen if the loop wasn't there? There'd still be a change in the flux around any loop you want to make in there. It's a flux in air. Or if we pump all the air out of this room, you know, we got a pump, we'll do that in a couple of seconds. No. If we had a vacuum, you'd have an electric field around a loop in a vacuum. Okay. And that electric field would collapse. When the electric field collapses, it creates a magnetic field. Then collapses and creates an electric field, which then collapses and creates a magnetic field. And that's how you can see me and I can see you. That's where electromagnetic radiation comes from. So that's something that we're not going to be able to get very deep into, but it's a neat idea, so it's worth thinking about. Okay, we just make this spike. we create electric field around any loop you might want to see. The electric field collapses, and then there's a change in electric flux, which creates a magnetic field, which then creates an electric field when it collapses. Okay, and that's the essence of electromagnetic radiation. There's a lot of detail to it. And I found it pretty difficult to get my head around. I mean, I could understand the Corning vectors and all that stuff. Still, I didn't have the ability the first time I saw it to figure out the relative orientations of the field. I knew what they were supposed to be, but it didn't quite gel for me. Well, if it didn't gel for me, I'm going to assume it's probably not going to gel for most people in an introductory physics class at this level. Okay, in the time we have. We spent a good week on it. Yeah, I can tell you this. Depending on your ability to visualize certain dimensions to it. And if not, you could just manipulate the equations. We don't have that much time. There's one thing to be disappointed with. Okay, now did really well for us. Okay, saw almost everything. Got hung up on that cosine theta, which you didn't need. We never used cosine theta because everything was always oriented parallel or perpendicular to the axial vector. Okay. Had there been some orientation or you weren't parallel to the axial vector, then you'd start wanting to take account of that. Although if it's off by just a little bit, the cosine of a small angle is still pretty close to 1. But when you start getting past 20 degrees or so, it starts getting significant. So it's worth thinking about. Okay, well, let's talk about the chapter at hand. But since that's what we did in lab, I thought it was worth trying to get a handle on it. And incidentally, in lab, I think we were only seeing, we also had spikes in the voltage, the potential. They were in the order of millivolts. This is on the order of almost in the order of volts. And I haven't reconciled that. I need to get my hands on the equipment and play around with it and see if I get it to behave the way I think it ought to. But not really seeing that there's a way. Okay. Okay. Now, some time ago, told you liquid force on charge Q moving with velocity v is QV cross B. I L cross B. I'll make that an I delta L cross B. That would be the force on a small segment of current, I of length L. Has some direction. Okay. And we've actually worked out stuff with both of these. One consequence of the QV cross V is if QV, oh man, I hate that wasn't in focus. That was so profound. Thank you. That's pretty good. Okay. That reminds me a little bit of, come on, camera. Look, there's I guess it doesn't look. I was reading, I'm reading, oh, here's rereading about the third time and understanding it much better than before. Uh, the novel Moby Dick, which is and has been for a long time, reputedly the best novel ever written by an American. Seen a lot more depth. When I read it as a teenager, I just interested in what's going to happen to the boy, what's going to happen to these people. And there's a scene in there where the boom in the sail becomes loose and swinging back and forth really fast, and it'll kill you if it hits you, or at least it'll knock you into the water and you'll drown. Okay. And this harpooner takes a dive and crawls under the plane of the boom, runs over, lassos it, secures it, and then dives into the water to rescue this guy who just tried to kill him, who got knocked into the water by the boom. He became accepted by the crew after doing that. Now, the way you crawled under there, okay, that just brought that to mind. So, you apparently belong in a great American novel somewhere. So, let's hope that happens. Okay, I've been recording that raving, but there we go. Let's say again what I said before it got blurry. You got F equals QV cross V. Okay, this is something we're familiar with. I'm a little less familiar, but we've seen it. Same time we saw this. F equals I delta L cross B. I is a current in a very small short segment of wire, or some current segment of current. Could be an electron beam in a vacuum, could be a lot of things. Okay, but it's going to have a direction. Make the segment short enough that it specifies direction. And if it's a continuously changing direction, you're going to integrate this thing anyway. All right. So that's basically how charges respond to magnetic fields. Okay. And then we have the rule for the magnetic field that you get from a charge. That K prime times I delta L cross R thing. Okay, comes later. But it's two sides of the same coin. And I forget where I was going to go with that. So let me just continue with a summary. And I do want to keep looking at the chapter review, so I'm make sure I'm using my appropriate notation. Yeah, when I saw the blur, I was just about to suggest, okay, this is an example. If QV is in that direction, and the magnetic field is in that direction, we do QV cross B and we get the direction of the force. Particularly if we have a loop in a single plane, then every we back up thinking of a loop. But okay, forgot QV cross B. Let's say, okay, QV is in this direction and B is in this direction. Okay, so QV cross B is in this direction. Now, what happens if we're in a vacuum and that charge moves a little further? Well, it's going to have a force on it that's perpendicular to its direction, because it's got to be perpendicular to both the direction of the QV, its velocity basically, and the magnetic field. So it's going to be centripetal. It's going to change the direction of the motion. And if QV doesn't have any component, if the component, if every component, if QV is perpendicular to B, then your motion is not going to change It's plane, it's not gonna go up or down. If it's straight, flat, horizontal, it's gonna stay horizontal in a vertical magnetic field. So it's gonna have a centripetal acceleration, which is gonna change its direction. It's not gonna change its speed because a force perpendicular to the direction of motion does no work. It just changes the direction, okay? So the direction is going to be continually changing at the same rate. The velocity is going to, the speed is going to remain constant. So things got to go in a circle. Okay. So if QV is perpendicular to V, is perpendicular to both V and V, equals QVB, then the centripetal force and the motion will be circular. Now there's another condition on this that I'll throw in there in a minute. With mv squared over r equal to QVB, because mv squared over r is your centripetal force, v squared over r is your centripetal acceleration. Write this for reasons it might not be. That's your charge to mass ratio. Times your velocity over your magnetic field. In other words, the other velocity needs to be in a plane perpendicular to V. So F, V, and V are all mutually perpendicular. In that case, you would have this. And if you then have a vacuum tube that you can put a voltage on, and if you heat the cathode, which is the terminal that'll eject electrons when it's needed, you know the potential difference between the cathode and the anode. The electrons will run through the vacuum, the cathode to the anode. And then back along the circuit, they'll just keep circulating, okay? If you do that, you can very precisely control the voltage to which those electrons, well, the voltage difference between the cathode and the anode, okay? You get the force gradient for the electrons, you can figure out how fast they're moving, okay? Then if you use a set of coils or whatever, with magnetic field perpendicular to that one way or the other, it's going to deflect that beam of electrons. And typically you have a phosphorescent screen down here, so you can see how the beam of electrons, when you impose a magnetic field, no longer hits here, it hits down here. You figure the radius of curvature, and you can figure out this radius. So you can figure out the charge to mass ratio of your electron. Okay? It's a big deal. That was done around the turn of the century. Then if you do Millikan experiment, you can figure out the quantum charge, and I'll do a couple of other things. Run this thing through a cross electric and magnetic field to get a known velocity. Put all that together, and you can then figure out both the charge and the mass of the electron. It's a pretty neat experiment. You'll see more about that. What I'm not sure of is whether I'm seeing the way to make this thing go away. Oh, wait, may think it's that's not it. I knew that a while ago. Okay, well, I don't get to see the whole screen. There's something I need to make go away, but I think it will show. Okay. So I'm not going to go through all the details of that. That's just a typical application of this one. If you want the force on a segment of wire and a magnetic field, just use this. Okay. And it's pretty simple if the wire is a straight segment and the magnetic field's uniform. Otherwise, you gotta do it. Okay. You gotta be able to set up that in. Now, this is all stuff that we've talked about. Let's say you've got a current around a square loop of wire. Say you've got a magnetic field. Say your magnetic field is acting downward in the plane of that wire. Then what's the direction of the force exerted on this upper segment? Perhaps the right hand rule. Yeah. I is in this direction. B is in this direction. If you cross I with B, you get a force out of the board, right? You agree? I'm not sure if you're making obscene gestures or what. But your hand keeps moving around so fast I can't even see. No, seriously. Okay. IL cross B. I in this direction, B in this direction. There's your force. And we've got a hand up. So either I did something really dumb or somebody needs something clarified. Okay. Now what about on the lower end? Well, now the current is in this direction, the magnetic field's in this direction, and the force is into the plane of the board, right? So it's being pulled out of the board here, it's being pushed into the board, it's being rotated. Going to tend to rotate until what? Well, let's think a little more. First of all, what's going to happen here? Well, there's not going to be any magnetic force because the cross product two parallel vectors is zero. Okay, so I delta L cross B out of the board, this face, I delta L cross B is in the board on this face, but on this segment and on this segment. So side view, got a force here, force here. Assuming the magnetic field is constant everywhere, then the magnitude and also perpendicular to delta L, which is why I've drawn it. The magnitude just got to be ILB because the sine of theta is 1. Okay. In other words, the angle between your magnetic field and your delta L is 90 degrees. The sine of theta is 1, so you don't have to worry about I delta L times B times sine theta. Sine theta is taken care of in this case. If this distance is L, then it's the torque. Well, moment arm's L over 2, force is ILB. Moment arm down here is L over 2, force is ILB. The torque is, as we orient this way, torque is um, out of that with the units. This is a square loop. Does L squared make sense? Well, if you double the dimensions of the loop, you're going to double the force on each of these segments, and you're also going to double the moment arm. So your torque is going to fall. Okay. In other words, by whatever factor you increase L, the force increases by the same factor, and so does the moment arm. So it makes sense that you have an L squared there. Okay. If the loop is rectangular, well, you can read about that in the book. That's pretty easy to understand. Now, if this loop is horizontal, it's the magnetic field acting down. if the loop is in the plane perpendicular to B, then if the field is into the loop, and let's just take our delta L to be counterclockwise, fields into the loop is into the loop, delta L is like this. So your delta L cross B is like this. Delta L cross B gives you a force out. Okay. You see that if B's in this direction, the delta L's in this direction, then delta L cross B is like this, cross with this, which would be upward. Like so. I'm not going to go through the details. Your book has good pictures. Okay. And then when you come down here, your delta L is in this direction. Your B is here. So you got to do delta L cross B. Wait a minute. There's delta L. And you cross that with delta L. And you got to cross that with B. You got to turn your hand like this. And the force is like so. Similarly, you argue by symmetry. Magnetic field would tend to expand this thing. Okay, would tend to deform your loop. If your loop's made out of solid, strong material, it's not going to deform. It's going to make much change. Okay, now if you were running magnetic or the electric field in the opposite direction, it would tend to compress the loop. Right. So it would stress the loop, but there'd be zero net forcing. And there'd be no force and no torque. So I need a loop. Something. Okay. That paper's too big. That's totally unimportant. Okay. So if this is your loop, and your magnetic field is in this direction, with current flowing like so, the loop is going to tend to be turned this way. Now, if the loop is here and the magnetic field is straight down, well, the loop is going to either tend to be expanded or contracted along all sides, but it's not going to tend to rotate. So this thing ain't going to rotate. If it's here, it rotates. It's here, it doesn't. If it's somewhere in between, it rotates, but with less torque. And all that should be made clear just for understanding the right-hand rule and looking at the diagrams in your textbook. If it's not clear, we'll demonstrate it some more. If run the current, well, let's just say, if we're running the current, okay, if we're running the current from here to this point, this thing is going to, if it's on some good bearings, it's going to continue to try to rotate. Okay. But at some point, we want to reverse the current. So we continue to get a torque in the direction of motion. Okay. If the current is running like this, which would be counterclockwise here, well, then it's running clockwise when it gets down here. So what you want to do is switch the current when it gets here. So it'll continue to accelerate down here. Okay, and all the way around to here, at which point you want to reverse the current again, come around like this. I don't know if you've seen those neat little motors you make out of a 10 cents worth of wire in a battery. You make a simple little motor. All you need is a commutator. Commutator is just an open part of a ring. I'm not going to try to describe it with hands. You can look at the pictures, and if you want, if we can do it quickly, we can try to even build one. Okay, very simple to do. You just scrape the wire the right way. You get a pretty neat little motor. A little hard to do with this magnet wire. It's kind of thin and hard to work with, but can actually be done. Okay. Well, we're running short on time, but let's see if there's anything else. Now, most of what I'm talking about is just an extension of stuff we've already talked about, you've already seen.